Okay, welcome to Introduction to Astronomy. We're going to try something a little bit experimental here. I'm using an Osmo camera. This is the first time I've done this. It's the first time I've actually recorded a video of one of the presentations. So we'll see how it goes, and hopefully I won't make too many mistakes, and hopefully we'll get a pretty good image of this. So this is the PowerPoint, or one of the PowerPoints that are available on Blackboard, and essentially all the content of this course is really taught primarily from these PowerPoints and secondarily from the textbook where there's a link available for the textbook. But I primarily use the PowerPoints which I've created and sort of center the course around. So in any case, this is our first chapter. This is the night sky. There is a preceding introduction to this course which talks about our place in the cosmos, but this is really chapter 1. So when we look at the nighttime sky, we're really looking at objects that are so far away from us that our depth perception doesn't allow us to really judge their distance. So everything looks equal and distant. And when we think about, an object, a geometrical figure of equal distances, we think of a sphere. If everything is the same distance from us, it traces out an imaginary radius in 3 dimensions. And that's what we call the celestial sphere. So it's sort of a model of what we see, even though if we look at, again, that first introduction that we did, objects in our solar system are much closer than objects which are in a local part of the Milky Way, and of course galaxies are much further away from that. So in any case, looking at the nighttime sky, we're going to look at why the sky appears the way that it does, especially in daylight. We'll look at the celestial sphere as a model for what we see. The sun, its position in the sky, not so much the physics of the sun, but more how it appears to us. The moon, how it appears to us. Stars, how they appear to us. The planets, other objects, comets, asteroids. And then finally we'll talk about eclipses. Unfortunately, we don't have many opportunities in the near future for eclipses, but we'll talk a bit about that. So, in any case, the sky, some people think this is a philosophical question. Why is the sky blue? And of course, the answer comes in a variety of things. Really, I think the answer to the philosopher's question is the sky is blue because that is a property of the sky. There is no reason for it. But really, if we understand the physics of what's going on, we notice that the sky is blue normally during regular hours when the sun is high enough in the sky, and then the sky appears to get sort of a yellowish, orangish, and a deep red in some cases. And this all has to do with the ways that molecules in our atmosphere will scatter light. So looking at this, how do we understand that we get these particular colors when in fact the light from the sun is pretty much white? Yet we think of the sun as being yellow, but in fact it biases a little bit to the yellow, but for the most part there's all colors of the spectrum, and this becomes evident during a rainbow. So why blue during the day? Why some of these reddish, orangish colors during the sunset or sunrise? Well, it really has to do with the molecules themselves. The molecules actually have a resonance in the ultraviolet, okay? They like to vibrate at the same frequency that ultraviolet light vibrates, okay? We'll talk a little bit more about electromagnetic waves later on. So, when sunlight hits them, and white light being all parts of the spectrum, red, orange, yellow, green, blue, violet, it is the shorter wavelengths, the blues and the violets, which cause the greatest interaction with the molecules, so the molecules are going to scatter that light the most. So when we pass white light through a collection of air molecules, they will scatter a lot of violet light, a lot of blue light, less green, even less than that yellow, and then finally it scatters red light the least. So when we look at the light, from the sky, it is not the light directly coming from the sun, but the light passing through the molecules, scattering off the molecules, and then making it to our eyes. If we look at the spectrum of this light, we probably would understand if I said the color is sky blue, okay, sort of a robin blue. It does contain all parts of the spectrum, okay, but it's not white light. It's this light blue, because if we think about white light as being all colors and blue being, of course, that part of the spectrum, we have more blue light than red light. So to our eye, as we interpret this light, even though it has red in it, has all colors in it, it appears to us as light blue. So that explains why the sky is blue. We're passing white light through it. The air molecules will preferentially scatter the shorter wavelengths, okay, and less so much on the redder end of the spectrum. Okay, so that explains why the sky is blue during most of the day. But at sunset, something different happens. If we think about light passing through our atmosphere, when the sun is directly overhead, it's passing through the least amount of our atmosphere. Okay, it's a direct trip straight down. You think about our atmosphere as being a thin shell around the Earth. Okay, the shortest distance is when it's coming down perpendicularly. When the sun is at a very steep angle, it is forced to pass through a lot of the atmosphere. So what happens is, what is initially white light from the sun gets scattered more and more. We're losing more and more red light. So what we're left over with are the longer wavelengths. We're left over with red light, we're left over with orange, yellow, green, and this gives it a yellow appearance. So as the sun gets lower and lower, we'll notice that the sky, especially around the sun, will begin to change from a bluish appearance to sort of a yellowish appearance, and then it passes through more of the atmosphere. It's getting lower and lower in the sky. It appears orangish. And in the case where there's a lot of aerosol particles, there's a lot of dust, there might be a lot of haze particles, smog particles, those scatter even more light, especially the shorter wavelengths, or absorbed with the shorter wavelengths, and we get those really deep red sunsets, especially if there's been a forest fire, or just in the summertime where there are a lot of aerosol particles in the air due to photochemical reactions. So, sky is blue during the day because air molecules like to scatter blue light. The light from the sunset appears to be more reddish because it's passing through more of the atmosphere, and the blue light has been pretty much scattered out before it even gets to us. So again, watching the sun high in the sky, it has a nice bright white appearance. As it sinks deeper and deeper to the horizon, it's passing through more atmosphere, gets yellow, orange, and again, in the times where there's a lot of particles in the atmosphere, not just pollution, but just general particles in the atmosphere due to natural effects, we will get this reddening that you see here. And I showed the sun being a little bit flat here. That's actually due to refractive effects that happens. Okay, so air molecules scatter blue light more than other particles. Well, what about clouds? Clouds also have particles in them, okay? These particles are condensed water drops. The water vapor has gone from the vapor phase to the liquid phase, but they're still small enough that they're suspended in the air. Why don't they scatter more blue light than other wavelengths? Well, here's the key here. Rayleigh scattering, which is the technical term for what air molecules do, will scatter shorter wavelengths more than it will scatter longer wavelengths. Read that as scattering more blue light than red light. As we get to larger particles, we go from molecules, and the Earth's atmosphere is primarily made out of diatomic nitrogen and diatomic oxygen, 2 nitrogen bonded together, 2 oxygen bonded together. Okay, very, very small particles. As we go to larger particles, like water particles that we have in clouds, those are much larger than the wavelength of light. So they have no preference in what they scatter, okay? Smoke particles, some of them are fine enough that they'll scatter more blue light, but for large particles like the water droplets, which are in clouds, they don't care what wavelength it is. They'll scatter light the same across the spectrum, and thus, because they scatter all wavelengths of light equally, they appear to be white. Okay, so daytime. This is astronomy. We're more interested in nighttime, of course, but I do have to emphasize here that when the moon is out, okay, the sky isn't completely black. It sort of has almost like a midnight blue color to it, because the light from the moon is actually being scattered by the same air molecules. Okay, so without the sun, there's less light to be scattered. So our sky goes from blue to dark. Okay, if the moon is present, there's some moonlight that's being scattered. But if we want a dark sky, we want as little or as few light sources as possible. Now, notice the sky during a full moon. Go out there sometime. If you can get away from the city, the sky is brighter than a normal nighttime sky would be. Again, because even though the moon is 1,000,000 times less brilliant than the sun, there's still enough light to be scattered, and it makes it hard to see some of the dimmer stars. When the moon is not present, again, we don't have the problem of light pollution that we'll address in a little bit, we get the darkest nighttime skies. Light pollution. Everybody thinks of pollution. We think of, dumping chemicals into the water supply, giving off aerosol particles into the atmosphere or gases into the atmosphere. These are different types of pollution. But light pollution isn't really putting a substance in the air. Okay, it's not really dependent so much on what is in the atmosphere or what is being put in the atmosphere. It is more dependent on sources of light. Now, when the sun is out, it is the greatest source of light. It overwhelms everything else. Sunlight is a very, very bright source of light, so it lights up the sky. When the full moon is out, it will also light up the sky. Okay? Light will go from it, it will scatter in all directions, and the atmosphere will basically, in scattering the light, appear to be light. We also see the same effect when we're near the city, when we're in the city. This is obviously a cityscape at night, and we see not only the glow happening from the ground, but as that light goes up the atmosphere, it's scattered back to us, and this produces light pollution. Okay? Now, this is not really something that we like in astronomy, because as the sky gets brighter and brighter, it becomes more difficult to see different objects in the heavens. All right? Certainly, during the daytime, we can't even see any stars. On the brightest full moon, okay, it's more difficult to see the dimmer stars. Same effect in the city. Street lights, building lights, lights from homes, all of these contribute to more scattered light, lighting up the sky and making it more difficult to see the objects in the heavens. Again, the moon, planets, they're bright enough that we don't have to worry about light pollution really affecting, seeing those. But most of the stars, which are visible in more rural areas, are completely washed out anytime that we're in the city. Again, it's the light from the ground sources which scatters off of the air molecules and, lights up the sky, making it difficult for us to see. This is a picture of North America at night, and we can clearly see where the population centers are. In this country, most of the population is really concentrated along the coast. The East Coast, the West Coast, And of course, there's quite a bit of population in the plains too. These are the areas where it's actually the most difficult to do backyard astronomy. And looking at our area, this is another satellite image, we can see the northeast corridor right here. And New York City is really the worst place in North America to try to watch the nighttime sky. Just a lot of ground sources of light because we're a very, very densely